This is it. You made it through the semester. Congratulations on learning the fundamentals of statistical analysis from an engineering perspective. Hopefully you've learned how the tools and techniques of probability and statistical inference can be applied to a variety of engineering processes and systems. As you could tell from the hours and hours you spent on homework assignments, we focused on understanding the fundamental tools of statistical analysis and gaining an understanding of what those tools mean and what they tell us in statistics problems. We talked about using computer tools to assist in the analysis, but our focus on fundamentals enables you to understand the results of computer output. You aren't some analyst who has memorized what to do when the p-value is small. You know what a small p-value actually means. And this fundamental understanding will pay dividends when you encounter statistics in the future. As engineers, where might you encounter some of the techniques learned in this class? Reliability engineers often fit probability distributions to failure time and repair time data, then analyze the results of those distributions, solving system reliability and component redundancy problems. Quality control engineers apply knowledge of probability and statistical inference to monitor the statistical behavior of processes and systems to determine if machine repairs and redesigns should be implemented. Oftentimes, the performance of processes and systems aren't witnessed in nature. They have to be simulated. Fitted probability distributions are used in discrete event simulations to simulate the conditions of processes and systems in many engineering contexts. And of course, we discussed several applications from materials to civil infrastructure to electrical systems to facility layouts and everything in between. For those of you continuing on in the data science and analytics program, these fundamentals will be vital. You'll learn about many other statistical tests where you'll be expected to know immediately what hypotheses are, what p-values are, and how to connect the two together to draw conclusions about a process or system. For example, in the Intelligent Data Analytics course, ISE 5103, you'll discuss linear regression, a means to model the linear relationship between a response variable y and a predictor variable x. A hypothesis that you'll address in linear regression has a null hypothesis statement that there's no relationship between y and x, and an alternative hypothesis statement that there's indeed a relationship between y and x, and that you can express that relationship with a linear model. You'll implement linear regression in R software, and R will provide a p-value output. The notion of hypotheses won't change, and the notion of a p-value won't change. Based on your fundamental knowledge of statistics, you'll be able to quickly draw conclusions about a technique like linear regression, or any new statistical technique that might come your way. We said that the field of statistics has been around for a long time. Techniques and variations on techniques have been developed for all different kinds of specific data situations. You have enough fundamental knowledge now to be able to pick up any of those techniques. And if you're not continuing on with further courses in statistics, and even if you never again apply any of the approaches we discussed once this course is over, do remember one thing. Most of the quantitative questions that we want to answer, whether we're engineers or not, involve uncertainty. Processes and systems exhibit random behavior. There's a likelihood that we witness a particular kind of behavior in a process or system. And if we try to describe that mean behavior with a sample mean, we're really just offering one realization of a random variable, as the sample mean itself is random due to the nature of sampling. Even if you never calculate a confidence interval or perform a hypothesis test, remember that sample statistics are random, and be cautious if you report a sample statistic as an estimate for a population parameter. Now that you've made it through the course, I'd love to have your feedback. Whether I'm teaching a course in a traditional classroom setting or in an online setting, I value feedback from students, and I make changes to how I deliver material based on this feedback. Please help me with your thoughts. I appreciate your hard work this semester. Best of luck with the rest of your educational journey.